All right, here we are, Chapter 2, talking about scientific measurements and prefixes for numbers, values, conversion factors. All right, lots of good stuff. So, let's get started. You ready?
Yeah, I'm ready.
Okay, here we go. So, physical and chemical properties are different from each other. Physical properties generally don't have to do with actually events that change the chemistry of a compound. Usually we might boil something or melt something, right? All of these, for example, water going from solid to water going to liquid. What do you call that process if I go from solid to liquid?
Solid to liquid? That's melting.
Very good. That's melting. Melting. And notice that the chemistry in between the oxygen and the hydrogen hasn't changed. We have the same compounds, both sides, all right? So the color, the different, the density, the electrical conductivity, these types of things are not related to an actual chemical change. They're just a physical property, all right? Chemical properties, generally, you can tell that somebody's talking about a chemical property because they'll use words like rusts, corrodes, oxidizes, decomposes, reacts with, right? So lots of these different properties are changing. I mean, all different chemical changes. Chemical properties have to do with chemical changes, right? So if something changes chemically, like if water decomposes to hydrogen and oxygen, all right, that means now the hydrogen and oxygens are interacting with each other in a different way. Okay? Very good. So, let's see if we can look at some of these and identify which kind of property we're talking about. What do you think?
Well, if magnesium metal is gray, gray is just the physical property. It doesn't have anything to do with it chemically.
That's right. How about tarnishes in air? Does that sound like something chemical?
Yeah, tarnish I think just means like rusts, like reacts with oxygen.
That's right. Very good. How about melts at 922?
Well, you said melting was physical.
Very good. Exactly. Going from solid to liquid doesn't change its chemical properties. Okay. How about reacts violently with?
Chemical.
That's right. How did you know?
Because it says reacts.
Very good. So reacts violently with hydrochloric acid. Excellent. All right. How about this one? Which of the following is a chemical property?
I would say B.
Okay, very good. Reacts violently with sodium metal. And I want to show you this video. Here we have a stand with some sodium on it, and we're going to drop it into this little kiddie pool of water. Watch what happens. Oh boy, that was quite an explosion, huh?
That's just sodium and water?
That's right, just sodium metal dropped into water. Okay, so again, looking at something like going from liquid to solid, we're not changing the atoms or the molecules. All we're doing is slowing them down when we lower the temperature. Here's some information about physical changes between the different states. And watch this video and you can learn some new words about the physical transitions.
Found in any of four states: solid, liquid, gas, or plasma. Solid can be changed to liquid by melting. Solids can change directly to gas in a process called sublimation. Liquid is changed to gas by boiling. Gas can condense to liquid. Solids can be formed directly from gas by crystallization. A plasma is a group of positive ions and unbound electrons. Plasmas can be produced by energizing gases to give up electrons, as in this neon sign, and fluorescent too. The sun is also a plasma. Over 99% of the matter found in the universe is in the plasma state.
Do we ever talk about plasma in class?
Not very much. We don't talk about plasma much, and we don't have a little symbol in our chemistry books really that talks about plasma. Okay? But yeah, we talk about liquid, solid, and gas mostly, and we have something called aqueous. Have you ever heard of aqueous?
I think, does that mean like dissolved?
Dissolved in water. That's what aqueous means. Very good. Okay, so here's an example of a chemical change, right? We drop the chemical into water, and we have a separation. Here we're dropping HCl. We have a separation. The hydrogen goes with the water and forms H3O plus. New way that the metals are interacting, or the elements are interacting with each other. Okay, so there's an example of a chemical change. Again, our states: solid, liquid, gas, plasma. Well, you know, all of our light bulbs nowadays, not all of them, but most of our light bulbs are incandescent tubes, we call them, and they contain a gas at a very low pressure. And that gas, when a voltage is passed through it or applied to it and a current passes through it, then it will release light, okay? Release energy in the form of light. And so those are plasmas inside our light tubes that we have. All right, so let's see if you know anything about any of these 4 or 5 different scenarios and which one might be a chemical, which one is a physical change.
I think bleach dyeing something is chemical. Grape juice going sour, that's like making alcohol, so that's chemical. Sugar turns brown, is that physical?
Actually, that is chemical. When we oxidize sugar and make it taste a little bit different, that's a chemical change.
Okay. And burning is chemical, so D must be the answer. Cold weather. Oh yeah, condensation. Didn't they say condensation was what you get when you go from gas to liquid?
That's right. That's right. Condensation is when you go gas to liquid. So that's an example of a physical change. Very good. Water boils on the stove. What's in the bubbles when they boil?
Is it hydrogen gas?
No, it's not hydrogen gas, right? For water to boil, to become hydrogen gas, that would mean that we're changing the bonds, right? If from this we're going to get hydrogen gas, we must get oxygen gas too, if that's what boiling was. But that's a chemical change, right? So if it's just boiling, that means we're just looking for a physical change. So it's got to still be what?
Oh, got to be water.
That's right. Still got to be water. Okay. Very good. Yeah, if you look at the bottom of a pan, those little bubbles, those are the bubbles, the liquid that is hot enough now to become a gas. Okay, good job. Now, whenever we talk about numbers in math class, we don't necessarily always have to have them get units. But in chemistry class, every number is associated with a measurement. Therefore, we should always have units with those numbers. Okay? There was an example of the importance of using not just units, but the correct units. In 1999, 2 labs were working together with a space probe, and the space probe was lost into Mars because they were using different units. All right? So just a little example of, yes, it can be very important to make sure you have the units. And anytime we're talking about numbers, we're not talking artistically. They're all measurements. They are a number. So they are a measurement. So we want to make sure we have the units. Okay? If we don't have units, we call that qualitative. Qualitative. I mean, if we're just looking for the presence of something like mercury or a toxin or something, and we say, yes, it's there, that's qualitative. But it's a step further to be quantitative, to say, yes, it's there, and this is how much is there. All right? So quantitative means we have the units associated with it. Okay? And now there are some common measurements that we use, which we call standard international units. And we don't always have to use these. I think that when they were first kind of strongly pushed, they were hoping everybody would adopt them and use them. And mostly people do. But in general, there will be a lot of scenarios in lab or in academia or in industry where they don't use standard units, and you have to be able to adjust. But you also want to be aware of what the standard units are that are out there. There's standard units for length, mass, temperature, right? And if you take these standard units and multiply them by each other, then the new units that are derived are just derived from the multiplication or the addition. If you do any sort of math with them, right, they will be changed, derived. So just like you would multiply the numbers, you have to end up multiplying the units as well, okay? Another thing that we want to become familiar with is what we call multipliers, decimal multipliers, or these prefixes, okay? They save us a lot of time. So for example, if I wanted to say, at first he said the particle was this big, so I was like, cool. Then he changed his mind and said it was that big. Well, to express this value here, it would take a lot of kind of communication, 0.000000001. People wouldn't be able to hear you very well. So we say things like nanometers, right? Or 0.01 nanometers. If we keep our values between, 1 and 100, then that usually allows us to communicate more effectively, okay? So we want to become familiar with some of these prefixes. I think that you are already familiar with some, like centimeter. When we were kids, we looked at and we identified the length of a centimeter. Okay, so here I have a ruler down here. And you can see each one of these units, 1 to 2, is a centimeter, right? Hopefully you're familiar with that. And also the ticks in between the centimeter, right there, right? The little ones, there's 10 of them each centimeter. Those are millimeters, okay? Centa, like century, 100, or cent, like a penny, right? 100, that means there's 100 centimeters for every meter. And if there's 10 millimeters per centimeter, that means there's 1,000 millimeters per meter. So what that helps us with is know how we have to, how many millimeters, what we have to multiply by to go from millimeters to meters. And over here is what we call the multiplication factor, 10 to the minus 3 for millimeters, or milliliters even, right? 10 to the minus milligrams, 10 to the minus 2 for centa, okay? And then nano kind of sounds like 9, so that's one that's easy for people to remember. 10 to the minus 9th, a nanometer. 10 to the 9th nanometers for meter, or 10 to the minus 9 meters in each nanometer. Okay, think about what I just said and play it over if it didn't quite make sense. And then micro is one that usually gets skipped. Usually people know a little bit about milli. They've heard of nano, but they forget about micro. But micro is 10 to the minus 6. And essentially what these numbers mean, minus 6, minus 9, minus 3, means you take the value 1 and you move the decimal place to the left if it's minus, and to the right if it's a positive value, right? Okay, so we want to become familiar with milli and centa really well. And then micro and nano are kind of the next most important. Pico, we won't hardly ever see. Kilo, that's probably just as important as milli. And so we got kilo and milli that we want to remember. Mega, giga, and tera, we probably won't see much. And really, as you get involved with software and saving files that are large, you'll know how large a kilobyte is, a megabyte, a gigabyte, and a terabyte, whether it's storage space or file size, okay? So these are values that you probably are aware of to a degree. All right, so let's see if we can fill out this chart then, following this pattern. So see, we have 10 to the minus 9 grams. That's a nanogram, okay? So how many grams would be a kilogram? Kilogram, do you remember?
Kilo was larger, right?
Yeah, it's larger.
Kilo's like 1,000?
That's right. So what would my number be here? How many grams?
10 to the minus 3 grams.
10 to the minus 3?
Yeah.
No, actually, it's 10 to the 3 grams. 10 to the 3 grams, because there's more grams than there are kilograms.
Oh, yeah, okay.
So 10 to the minus 12 grams? How many grams would we call that?
Minus 9 was nano. Minus 12. Is that the pico?
That's right. That's right. Picograms. So nanometers, 10 to the what?
10 to the minus 9 meters.
Very good. 10 to the 6 gram, what would we call that?
10 to the 6 gram. 10 to the third was kilo. What was 10 to the 6?
Was that big M? Mega? Mega, like megabyte?
Oh, yeah, kilobyte. 1,000 kilobytes is a megabyte. So megabyte.
Not megabyte, but mega what?
Megagram.
Very good. Megagram. Excellent. Microliter. What do you think?
It's 10 to the... We would want it in liters, right?
Yeah, liters. So is a liter more than a microliter or less?
Less. So it's 10 to the minus 6.
Very good. 10 to the minus 6 liters. HZ. Have you ever heard of HZ?
No.
HZ is hertz, which just means cycles per second. And you talk about hertz, megahertz, gigahertz of hardware, hard drive speed on computers. And we talk about it in terms of cycles of wave, electromagnetic energy in the future. So 10 to the 9th hertz.
Let's see. 10 to the 6 was mega. Oh, yeah. Gigabytes. So that's gigahertz.
Very good. Gigahertz. Excellent job. Well done. Good job.